Ever look up at the night sky and just feel small? Like you're peering into this totally unknowable abyss.
It's easy to feel that way. The scale is just immense.
Yeah, and measuring those distances, that's one of astronomy's biggest puzzles, right?
Absolutely. A fundamental challenge.
And if you're tuning in, you're probably someone who likes to, get straight to the point, cut through the noise.
Get the core concepts quickly.
Exactly. So let's dive right in. Today, we're digging deep into something called Cepheid variable stars.
Sounds specific.
It is, but they're absolutely pivotal. These aren't just any twinkling stars, they actually pulse.
Right. They get brighter and dimmer in a really regular rhythm.
And they live in a specific part of that big stellar family portrait, the Hertzsprung-Russell diagram.
Uh-huh.
Their pulsation periods, the time for one cycle, can range from just a day to over 100 days. It's like a cosmic heartbeat.
Is. And it's important to note there are actually two main families, you could say. First, you've got the classical Cepheids. Think of these as the youngsters, bright, high-mass supergiants.
Population 9, right?
Exactly, population 1. You find them in the busier parts of our galaxy, the main plane, the spiral arms, inside open star clusters.
Got it. Young and in busy places. What's the other type?
Those are the Type II Cepheids. These are generally older stars, lower mass, fewer heavy elements.
Population 2.
Population 2, that's right. And they tend to hang out in different areas, far above or below the galactic plane, in the central bulge, or in those ancient globular clusters.
And you mentioned subtypes for these type 2s.
Yeah, even within Type II, there are classifications like BL-HER, W-VIR, and RV-Tau. It mostly depends on their pulsation period. Different models within the Type II brand, as you put it earlier.
Okay, so two main types, different locations, different ages. How do the classical ones, the young ones, start pulsating?
That's a great question. They start out as really massive, hot, young stars types O and B on the main sequence, real powerhouses. As they evolve, use up their first batch of fuel, they expand and cool, and they pass through this region on the HR diagram called the instability strip.
Instability strip. Sounds descriptive.
It is. It's a zone where their outer layers just become unstable. They can't find a steady balance.
Yeah.
So they start to oscillate, expand, and contract, get brighter and dimmer.
And that's the pulsation we see.
That's the pulsation. And a key thing here, the more massive the original star was, the brighter it is, higher luminosity. And actually cooler its surface temperature is when it hits that strip.
Interesting. Now, you'd think, maybe naively, that you could just look at a star's mass and know its brightness, right? There is a mass-luminosity relationship.
There is, absolutely. And a radius-luminosity one, too. These are fundamental stellar physics relationships. But the problem for distance measurement is, well, you can't just look at a distant star and measure its mass or its radius directly. Not for most of them, anyway.
Okay. So even though those relationships exist deep down, they aren't the practical tool we need for finding distances.
Exactly. They're not directly observable. For the vast majority of stars, we'd want to use as distance markers.
Right. So we've got these pulsing stars, different types, interesting origins, but some key properties are hard to measure directly. What's our main goal here today? What are we trying to really understand about them?
Our mission, let's say, is twofold. First, we really want to get a handle on why these Cepheids are so incredibly crucial as cosmic distance indicators. They're like super reliable yardsticks.
Okay, the why of the yardstick.
And second, we want to explore what the latest data, especially from the Gaia mission, is telling us. Not just about Cepheids themselves, but about our whole Milky Way galaxy. Gaia's really shaking things up.
All right, Gaia's the game changer. But first, let's unpack that core idea, the yardstick.
Right.
Why are they so good for measuring cosmic distances?
The absolute key is something discovered by Henrietta Leavitt way back in 1908. It was an empirical finding. She just observed it.
What'd you find?
She found this amazing correlation. The period of a Cepheid's pulsation, how long it takes to go bright, dim, bright again, is directly linked to its actual brightness, its intrinsic luminosity.
Wow. So measure the timing, know the brightness.
Essentially, yes. Longer period means intrinsically brighter star. It's remarkably elegant. She saw the pattern, and later theoretical work actually explained the physics behind why it works.
But you mentioned earlier it's not perfectly clean, right? There's some scatter.
Exactly. Even when you account for things like dust dimming the light, the relationship isn't a perfectly sharp line. There's some spread. And that's mostly because that instability strip we talked about. It isn't infinitely thin. It has some width in terms of temperature.
Okay, so stars at the same period might have slightly different temperatures, affecting their brightness a bit.
Precisely. But astronomers figured out a clever trick. If you measure the Cepheids' brightness through different colored filters, get its color index, you can use that information.
To correct for the temperature difference?
You got it. Adding that color term really tightens up the relationship. It reduces that scatter significantly, letting you pinpoint the luminosity much more accurately.
So this period luminosity relation, maybe period luminosity color relation, it's fundamental for astronomers then.
Oh, absolutely revolutionary. Historically, it was the most accurate way we had to get distances to other nearby galaxies.
How does that work in practice?
Well, if you can spot a Cepheid in, say, the Andromeda galaxy, and you measure its pulsation period, you can use the period luminosity relation to figure out its true intrinsic brightness. Then you compare that true brightness to how faint it appears to us here on Earth.
And the difference tells you the distance. It's like knowing a light bulb is 100 watts. If it looks dim, it must be far away.
That's the perfect analogy. Exactly like that.
Okay, that makes total sense. So I guess astronomers are always trying to fine-tune this relationship, make the yardstick even more precise.
Constantly. There's a huge amount of ongoing work to really nail down the exact slope of that relationship, how much luminosity changes per day of period, and the 0 point.
The 0 point, what's that?
The 0 point is like the anchor for the whole scale. It basically says a Cepheid with this specific period has this specific intrinsic luminosity. Getting that anchor point absolutely right is critical for all the distances that rely on it.
And how did they even set that anchor point before we had super precise space telescopes like Hipparcos or Gaia?
Good question. Before Hipparcos, a key method was finding Cepheids inside open star clusters or associations.
Groups of stars born together.
Right. We have pretty good models for how stars in a cluster evolve. By looking at the main sequence stars in that same cluster, plotting their brightness and color, astronomers could use a technique called main sequence fitting to estimate the cluster's distance.
Okay.
And since the Cepheid is in that cluster, at the same distance, knowing the cluster's distance tells you the Cepheid's true luminosity. Do that for several Cepheids in different clusters, and you calibrate the 0 point.
Clever. Using the whole cluster to calibrate the special star within it.
Exactly.
Now, here's a potentially tricky question. Are Cepheids everywhere the same? Like, does a Cepheid in our Milky Way follow the exact same rules as one in the Magellanic Clouds, our neighbor galaxies?
That is a really important point. Are the period color and period luminosity relations universal?
Yeah, because if they're different.
It messes everything up. If Cepheids behave differently depending on their galactic home, maybe because of different amounts of heavy elements, different star formation history, then using a Milky Way calibration to measure the distance to another galaxy could be wrong.
So checking that consistency across different galaxies is crucial.
Hugely important. A lot of research effort has gone into comparing Cepheids in the Milky Way, the large Magellanic Cloud, the small Magellanic Cloud, and beyond to check for any subtle differences.
Okay, so distance letter cornerstone. Got it. But you also hinted they tell us more about our own galaxy.
Absolutely. They're not just yardsticks, because they're intrinsically very luminous stars.
You can see them from really far away, even within the Milky Way.
Precisely. We can spot them across large sections of the galactic disk. And remember, they're associated with young stellar populations.
The classical ones, yeah.
So where you find classical Cepheids, you're likely finding regions of recent or ongoing star formation. They act like bright signposts, tracing out the galaxy's spiral arms.
Oh, that's cool, like connecting the dots to see the pattern.
That's a great way to think about it. Mapping Cepheid locations helps us map the spiral structure.
Fantastic. What else?
Well, besides their position, their motion is incredibly informative. By measuring their proper motions, how they move across the sky over time.
Which space telescopes are good at?
Extremely good at it,
Yeah.
especially Hipparcos and now Gaia. Measuring these proper motions gives us a powerful tool to study how our galaxy rotates.
How fast different parts are spinning.
Exactly. Understanding galactic rotation is fundamental to figuring out the galaxy's mass, how that mass is distributed, the influence of dark matter, all sorts of things.
You mentioned Hipparcos earlier. How did it specifically help with this rotation puzzle using Cepheids?
Before Hipparcos, studies of galactic rotation using Cepheids were pretty much limited to our immediate solar neighborhood, just a small patch.
Right.
Hipparcos gave us precise proper motions for stars much further out. A key early study, I think it was Feast and Whitelock back in '97, used about 220 Hipparcos Cepheids And from their motions, they could derive these things called the Oort constants, A and B.
Oort constants. What do they tell us?
They're basically numbers that describe the local rotation characteristics, how the orbital speed changes with distance from the galactic center, and how the orbits are sheared. They give us direct measurements of the velocity field right here in our part of the galaxy.
Wow. So positions tell us structure, motions tell us dynamics. Anything else these amazing stars reveal?
There's also information in their vertical distribution, how far above or below the main plane of the galaxy they are.
How does that tell us anything?
Well, think about it simply. Young Cepheids are born in the thin disk close to the plane.
Right, where the gas and dust are.
But they're born with some initial velocity, including a component moving up or down away from the plane. So over time, gravity pulls them back, they oscillate up and down,
Ah, like bobbing on water.
sort of. And the time scale for one of these oscillations, maybe 70 to 100 million years or so, depends on the local density of how strong the gravity is pulling them back.
So a cepheid found way high above the plane is likely older than one right in the plane.
Generally speaking, yes. Its position off the plane gives us a clue about its age and the gravitational environment it's been moving through.
Okay, this is incredible. Even before Gaia, Cepheids were like Swiss Army knives for astronomers. Distance, structure, rotation, age clues.
They really were and still are fundamental tools.
But you keep mentioning Gaia, so how is Gaia taking all this to the next level? How is it revolutionizing things?
Gaia is just transformative. The precision is the key. It measures parallaxes, those direct geometric distances, with absolutely unprecedented accuracy.
Much better than Hipparcos.
Orders of magnitude better for many stars. And on top of that, it provides incredibly precise brightness measurements in multiple colors, taken over and over again across many years. Multicolor, multi-epoch photometry.
So better distances and better brightness and color data.
Exactly. It gives us this amazingly detailed, precise view of where these stars are, how bright they are, what color they are, and how they're moving.
Can you give some specific examples? What did Gaia find early on?
Sure. Even in its first data release, DR1, Gaia included data for about 600 Cepheids just in the Large Magellanic Cloud region. And crucially, these were observed really frequently early in the mission, which was fantastic for nailing down their pulsation periods very accurately.
Okay, a good start. And DR2, the second release.
DR2 was a huge leap. They developed a special processing pipeline just for variable stars, like Cepheids, and another type called RR Lyrae stars.
A specific object study, right?
That's the one. Initially, they used it to look hard at the period amplitude and period luminosity relationships, mostly in Gaia's main G-band filter.
But then they added color.
Yes. Later, they folded in the data from the blue, GBP, and red, GRP photometers. Having that color information is vital, remember, for refining the period luminosity relation and accounting for dust.
Right, the color term helps tighten things up.
Yeah.
And the sheer number of Cepheids in DR2 was massive, wasn't
It's
it?
just astounding. The final DR2 catalog included, get this, 9,575 Cepheids in total.
Wow, where were they?
Okay, so about 3,800 in the Large Magellanic Cloud, nearly 3,700 in the Small Magellanic Cloud, and over 2,100 scattered across the rest of the sky, the all-sky sample.
So, mostly in our neighboring galaxies.
The large fraction, yes. But what's cool is that even though ground-based surveys like OGLE had already found tons of Cepheids in the Magellanic Clouds, Gaia still picked up over 100 new ones there.
And did it find new ones in our galaxy too, or in other nearby systems?
It did. The all-sky sample, plus specific looks at globular clusters and dwarf galaxies, Gaia found about 350 new Cepheids in those systems as well. It was like a grand Cepheid census of our local cosmic neighborhood.
Incredible numbers. Did Gaia give us more than just positions, brightness, and periods?
Yes, for a good chunk of them, over 3,700 classical Cepheids, with periods less than about 6 days. DR2 actually provided estimates of their metallicity
Their chemical composition. How?
by carefully analyzing the precise shape of their light curves. How the brightness changes over the pulse cycle isn't just a simple up and down. There are subtle bumps and wiggles. Using a mathematical technique, Fourier analysis, you can relate the details of that shape to the star's chemical makeup.
That's amazing. The light curve shape tells you about its chemistry.
It gives us important clues, yeah, about the abundance of elements heavier than hydrogen and helium, which in turn tells us about the environment where the star formed.
Did Gaia spot any of the rarer Cepheid types?
It did. That special pipeline was also good at identifying things like double-mode Cepheid stars pulsating in 2 different periods at once, and also anomalous Cepheids, which are a bit weird and don't quite fit the standard picture.
Okay, so we have this massive, rich data set from Gaia DR2. I remember seeing a plot summarizing the period-luminosity relationship from that data. What did it show?
Ah, you're probably thinking of the plot from Clementini and collaborators in 2019. It was a really nice visualization. It showed the period versus brightness for all three samples,
Hmm.
LMC, SMC, and the all-sky Milky Way sample.
And it plotted apparent magnitude for the Magellanic Clouds and an absolute magnitude for the Milky Way stars.
That's right. And importantly, that first plot didn't correct for dust extinction yet. The points were also color-coded by Cepheid, type classical fundamental mode, first overtone, type 2s, etc.
What was the most striking thing about comparing those three groups on the plot?
The most obvious thing was the scatter. The period luminosity relations for the LMC and SMC looked pretty tight, like nice distinct bands. But the all-sky sample, the Milky Way Cepheids, it was much more spread out, much more scatter.
Hmm. Why would our own galaxy Cepheids look messier on that plot?
Well, Clementini and the team suggested a few reasons. One, maybe some stars in the all-sky sample were misclassified. Perhaps they weren't actually Cepheids. Two, dust. Extinction from dust is much more variable and significant across our own galaxy than looking towards the Magellanic Clouds.
Looking through the galactic plane versus looking out of it.
Exactly. And three, the initial analysis treated all stars as single stars, but we know many stars are in binary or multiple systems, which can definitely affect their measured brightness.
So Gaia's data was amazing, but that initial plot showed there was still work to do to untangle those effects.
Precisely. It highlighted the power of the data, but also the complexities in interpreting it, especially within our dusty, complicated galaxy. Subsequent work, like studies by Pepe and others, and independent checks on the catalog purity by Molnar, started digging into these details.
And Gaia's impact wasn't just about refining the period-luminosity relation itself, was it? You said it helps with other research, too.
Oh, absolutely. The DR2 Cepheid data kicked off a huge wave of research. For instance, Curvella and colleagues combined Hipparcos and Gaia DR2 proper motions.
Looking at how Cepheids move over decades.
Right. And by studying the tiny wobbles in their paths, they inferred that a very high fraction of classical Cepheids, maybe over 80%, are actually in binary or multiple star systems.
80%? That's way higher than I would have guessed. That must change how we think about their evolution.
It certainly makes us reconsider things. And other researchers used the Gaia data to map out the Milky Way's rotation curve with much better precision and coverage than before. People like Meraz, Kawada, Eblemet published papers on that.
Getting a better handle on how our galaxy spins.
Exactly. Others, like Skowron's group, look specifically at the vertical motions, how Cepheids move up and down through the disk, giving us clues about the disk's dynamics. And they also use the Cepheid distribution in motions to trace the galaxy's 3D structure more generally.
So mapping the warp and flare of the disk.
Things like that, yeah. Unprecedented detail. And finally, theorists like Marconi's group have been busy developing better theoretical models, like period-Wesenheit relations, tailored specifically for Gaia's filters.
Wesenheit relations, those are designed to be less affected by dust, right?
Correct. They combine brightness measurements in different colors in a way that cancels out most of the effect of reddening by dust. Using these refined relations with Gaia data lets us estimate individual masses for these pulsating stars much more reliably.
Okay, let's try and wrap this up. Cepheids. They're not just pretty pulsating stars.
Not at all.
They are absolutely fundamental cosmic tools. First, for measuring distances, thanks to Henrietta Leavitt and that incredible period-luminosity relationship.
The bedrock of the extragalactic distance scale for a long time.
Second, they act like tracers, helping us map out the spiral arms and structure of our own Milky Way.
Right, because they're young and bright.
And third, their motions reveal how our galaxy rotates.
Giving us insights into its mass and dynamics.
And now, Gaia, this mission, with its incredible precision, is just revolutionizing everything we thought we knew about them.
It really is. It's refining that crucial period-luminosity relationship, finding hordes of new Cepheids, telling us about their chemistry, their companions, their motions. It's providing an unprecedentedly detailed picture.
An incredibly detailed picture of these stars, our galaxy, and by extension, the universe.
Exactly. The accuracy is just phenomenal.
So here's a thought to leave you with. We're now measuring where these stars are and how they're moving with accuracy that would have seemed like science fiction just a few decades ago.
It's truly remarkable progress.
Given that, what's next? With this level of precision applied to these cosmic heartbeats, What huge discoveries about, say, the expansion rate of the universe, or maybe the detailed evolution and future of our own Milky Way, what might they reveal next?
Hmm.
It's kind of mind-bending, isn't it, that these tiny periodic flickers and distant stars hold the keys to potentially unlocking even deeper cosmological secrets. Something to ponder. Thanks for taking this deep dive with us.